Hey, hey. So, at this point in this course, you're probably thinking, sequences and series. What's the point of everything that we've been doing so far? Now, this course is definitely taking a very, very drastic turn from everything that you've dealt with in the past. In the past, you've talked about functions, and you've talked about continuous functions at that. And you've been doing calculus, and with calculus, you've been doing derivatives and integrals, and you've in the past looked at continuity, and you've taken limits of all of these continuous functions like x squared or sine of x or arctangent of x, or even some functions that have discontinuities like secant of x or secant squared x, and you've found derivatives, you've found antiderivatives, you've even taken things like compositions of square root of x squared plus 1, and then maybe divide that by 1, and you've been able to do stuff with these. Maybe to make this one a little bit nicer, we can say 2x. But the point is, you've been able to analyze domain, you've been able to graph some of these, you can talk about when this function is increasing and decreasing. You can do a lot of analysis with these sorts of things. However, a lot of the methods that you learn in differential calculus and in integral calculus is that you can take derivatives of a whole bunch of stuff. You can take derivatives of pretty much everything, but then when it comes to integrals, we get kind of stuck. There are methods for integrating a lot of different functions. For example, this one seems to require substitution. This one, we have an idea of what an antiderivative would be. Same with this one, but, if we were to write maybe 2 over x squared minus 5x, let's say minus 6, and we wanted to integrate this, we could do an integration by partial fractions, and that would be something that we could do. But then we get something like arctangent of x. And arctangent of x actually doesn't really satisfy any of the other strategies that we ever learn. You can look at trigonometric integrals, you can look at integration by parts, you can look at integration by partial fractions, you can try substitution, you can try a rationalizing substitution, you can try a trigonometric substitution. There is a whole bunch of strategies that we can just throw at trying to find an antiderivative for arctangent, but every single one of them fail. That doesn't mean that arctangent doesn't have an antiderivative at all. It just means that all of the strategies that you learn in an integral calculus class typically fail us. And so we need something slightly more powerful. And it turns out that what mathematicians decided to do was invent this concept of sequences and series. So, at the very beginning, we learned about sequences, and, we can write out a whole bunch of terms, and these sequences may converge, or they may diverge depending on if the limit as n approaches infinity of the terms exists or not. And then we very, very, very quickly shifted gears to series. And we found that a series may converge or may diverge not if the terms converge or not, but if the sum of all of the terms converges or not. If this sum, this shouldn't say exists, depending on if, actually no, that works. If this sum exists or not. One of the prime ways that we chose to deal with evaluating when a sum converges or diverges is we can make a new sequence called an nth partial sum. And this nth partial sum was a sum as n went from, as I went from usually 1 to n of a sub I, and then we looked at the sequence of partial sums. And this is a way to actually wrap both sequences and series into the same concept. We were able to determine when this infinite sum would actually converge or not, or diverge by looking at a sequence. But this typically tended to be difficult. To actually find a pattern for S sub n wasn't always the easiest thing to do. And so we changed gears again, and we looked at series tests. And these series tests were really meant to help us determine when a series converges or diverges without writing an nth partial sum. Because nth partial sums aren't always the easiest thing to actually write down. And so maybe we can do some nicer stuff to actually determine when a series might converge or diverge. Now, in my opinion, these series tests are very, very similar to looking at different integration tests and saying, oh, if we have this sort of an integrand, then we can use integration by parts. In the same sort of strategy, if we have a series that is an alternating series, then we can use an alternating series test to determine whether this series converges or diverges. And so we've learned a whole bunch of these different series tests. We learned a test for divergence, we learned p-series, we learned geometric series, alternating series, telescoping series was in here as well. Telescoping series, however, was one of the rare ones that we actually had to go for an nth partial sum. We haven't learned Taylor series yet, but we will get to that in just a moment. There's also the comparison test, limit comparison test, the integral test, and the ratio test. There's also a root test, but we're not really focusing on that one in this particular course, but it's a possibility. In any case, we have a lot of different strategies that will help us determine when a series will converge or diverge, and that really helps us achieve our goal. But again, what was our goal? If we go back to the beginning here, seems like our point is to try to find antiderivatives. This is a calculus course, and so we want to actually focus on calculus. And it doesn't look like we've actually done any, integral or derivative or differential calculus in this particular course so far. So again, what's the point? Well, in my opinion, the point is we want to integrate. We want to integrate a whole bunch of functions that we may or may not have been able to integrate before, such as arctangent of x. We develop all of these different strategies, but none of this has anything to do with arctangent or integration until we get to Taylor series. Now, Taylor series, this is probably the most important topic in this chapter entirely. When we're talking about series and sequences, we really are trying to lead to Taylor series. And Taylor series are invented for us strictly for this one idea. Can we represent a familiar elementary function f of x, something like arctangent or e to the x or sine of x, that we may or may not be able to integrate as a power series, which we can definitely integrate. Now that's the big key here, in my opinion. We are looking at a whole bunch of different functions, and in integral calculus, we hit this brick wall in that there are a whole bunch of functions that we can't integrate. So, if we can actually express that function in some other way, in our case, a power series, then we will actually be able to achieve our goal of integration. Now, in Taylor series, what we're going to be doing, and once you go through the actual video for Taylor series, this will make a lot more sense, but I want to give you some motivation. What we're actually going to be doing is simplifying this summed, because this is actually going to be a very, very desirable form. This particular form is what dictates a Taylor series, and if we even look back at this series convergence divergence flowchart and we zoom in on Taylor series, we will see this very familiar a sub n. And I only say very familiar because I looked at it, 10 seconds ago. There it is. Here's this form that we're going to be looking at. Then we're going to actually simplify this, and we're going to use a series test to determine when this sum converges, or maybe when it diverges. Again, this is going to make a lot more sense when you actually go through the next video, but here's going to be our typical strategy that you can double back to. Typically, we're going to be using the ratio test. And the ratio test will tell us when L is less than 1, we get convergence. When L is greater than 1, we get divergence. and then when L is equal to 1, we have no idea. It's completely inconclusive. And so, when L is equal to 1, we get this inconclusive result, which means that what we do next is that we're going to end up having to plug in the appropriate x values that will make L equal to 1, and then we'll use a different series test to determine whether we have convergence or divergence. So when we're actually generating a Taylor series, our strategy typically will be write down the Taylor series. I'll even write this down. Write down the Taylor series. Once we do that, we want to use the ratio test. And this will tell us that we get convergence to determine convergence or divergence on an interval. But what's going to happen each time is that we're going to get an open interval, and we're going to need to test the endpoints of that open interval using a different test. So this will be the strategy that, again, I would love for you to double back to this particular video to get an idea for how to go through these different Taylor series types of problems. But then there's still going to be this big open question that may or may not seem evident to you. But one of the big questions that comes up is, when can we do this and why can we do this? And one of the big answers is Taylor's inequality. Now, a lot of the reason that I want to make this video is because when you're going through, there's going to be a lot of theoretical denseness. And a lot of that is going to round around this question of, when is this actually possible? When is a function actually equal to its Taylor series? Because we'll be able to generate a Taylor series, but we won't really know when a function is actually equal to that Taylor series. And one of the big questions as to when is this true is using Taylor's inequality. Taylor's inequality will tell us when our function, f of x, is actually equal to its Taylor series. That is, Taylor's inequality will tell us when we can actually do everything that we're doing. Taylor's inequality isn't the easiest thing to deal with, and so what I really want to also push is that whenever we're trying to answer when is a function equal to the sum of its Taylor series, there's really 3 different tests that we can use, and they're all the estimation tests. Now, I strongly recommend try the alternating series estimation theorem because it's the easiest of all of these different estimation tests. If you don't have an alternating series, then if you can, try the integral test. The integral test will typically be evident to use when you can actually find an integral for your summand. Lastly, if none of those work, then Taylor's inequality will work. It's just not the easiest thing to use. So, just to round out everything, what's the point? The point of all of this in sequences and series is that we want to do calculus on a function. But if we can't do the calculus on the actual function, then let's turn it into a series. And if we can do that, then we can continue our analysis and we can continue along with calculus instead of just hitting a brick wall and saying, we can't do this, let's give up. So there is a point to all of this, but it's not always the most evident thing to do. The point is, you're in a calculus class, we want to do calculus. If we can't do the calculus on the given function, then maybe we can turn it into a series and we can continue our analysis. All right. Thanks for listening, thanks for watching, and go ahead and give the next video a shot.